Video streaming platforms such as Netflix offer a convenient way to watch video content online. We're now able to watch our favorite TV shows, movies, and content creators on a range of devices. However, buffering while watching the video can be a painful experience on mobile phones and tablets that use 4G or LTE. As streaming becomes available to a wider range of devices with varying bandwidth restrictions, different encodings of the video need to be created for different devices. And these different encodings of the video can also compensate for different bandwidth situations. To get the best quality viewing possible with the bandwidth available to whatever connection a user is on, there needs to be a balance between the resolution of the video, the bit rate, and everything else that defines the data that the video consumes. Mux is a company that builds video hosting and analytics. Today's guest, Ben Dodson, is a data scientist at Mux, and he built a system for optimizing the bitrate of videos through machine learning. In this episode, we discuss video encoding and how Mux solved the problem of serving the highest quality video with the ideal bitrate. Azure Container Service simplifies the deployment, management, and operations of Kubernetes. Eliminate the complicated planning and deployment of fully orchestrated, containerized applications with Kubernetes. You can quickly provision clusters to be up and running in no time, while simplifying your monitoring and cluster management through auto upgrades and a built-in operations console. Avoid being locked into any one vendor or resource. You can continue to work with the tools that you already know, such as Helm, and move applications to any Kubernetes deployment. Integrate with your choice of container registry, including Azure Container Registry. Also, quickly and efficiently scale to maximize your resource utilization without having to take your applications offline. Isolate your application from infrastructure failures and transparently scale the underlying infrastructure to meet growing demands, all while increasing the security, reliability, and availability of critical business workloads with Azure. To learn more about Azure Container Service and other Azure services, as well as receive a free ebook by Brendan Burns, go to aka.ms/sedaily. Brendan Burns is the creator of Kubernetes, and his ebook is about some of the distributed systems design lessons that he has learned building Kubernetes. That ebook is available at aka.ms/sedaily. Ben Dodson is a data scientist at Mux. Ben, welcome to Software Engineering Daily.
Thanks, Jeff. Great to be here.
This conversation is going to be about a specific machine learning use case, and I think it's going to be a great example for why machine learning is so broadly applicable, because this is an application of machine learning to improve another area of software engineering, which is video encoding. So in order to get to the machine learning part, we need to start with that topic, the video encoding subject. What is video encoding?
So video encoding is basically when you take a source video and you decide to encode it along what's called a bitrate ladder. So usually the raw video file is huge. It can be hundreds of gigabytes, and it doesn't make sense to stream that to the client because it would just, you'd have rebuffering for hours, essentially, right? So a process that many streaming sites do is something called transcoding, in which you encode the video down to lower bit rates, let's say like 1 megabit, 2 megabits, 3 megabits streams, in which your internet connection could actually handle that size of video. And in order to do that, it goes through some sort of compression algorithm. So that's what you hear, when people talk about H.264 or, the AV1 is sort of this new compression technology is coming out in a few years. They're compressing down the video to a more manageable size and putting that in what's called a manifest for you to then choose sort of the appropriate size file that your bandwidth internet connection can handle. And so how you decide to do encoding, there's a lot of different settings that can go into encoding, and how you decide to do encoding can have a big impacts, on the type of video quality that you see.
Encoding is a type of compression, and we're not talking about a compression like a zip compression where you can't read the file without decompressing it. This is a type of compression like MP3 compression versus a WAV file. Like this is like a lossy format versus a lossless format where you can actually play back the file. You can read the file, but it is a slightly degraded format. And the reason you want to do that with video files is because video files are tremendously large, and depending on what kind of device the user is using, depending on what the connection the user has, depending maybe on the screen size, you want to use a different encoding mechanism that is customized for the user in the given user's context. Is that accurate?
Yes. Yeah.
Okay. So with an audio file, my source audio gets compressed into either MP3 or WAV or AIF, and in these video files, it's getting compressed into different files. It's not different file formats though, right? It's just different bit rates of the same format.
Right. It's all still the same format. It's just that the bitrate basically determines sort of how much information gets processed for each frame. So you have essentially a set number of bits that you can allocate, let's say, to each frame. And so for high bit rates, you can put a lot of the details and the motion will be in there. Whereas for the lower bit rates, you have to do sort of more with less. And so depending on how good the compression algorithm you're using, you might be able to get away with that down to fairly low bit rates. But it also depends very much on sort of the content of the video that you're looking at, which is where per title encoding kind of comes into play.
Right. We will get into that. But if we're ignoring that for a second, if we're just talking about broad encoding mechanisms, so if I'm streaming video from my home connection and maybe I've got a T1 connection and I've got super high bandwidth, high performance network connection, and I want the highest quality video versus maybe I'm sitting on my phone in the middle of nowhere and I've got a really spotty connection, but I still want to stream House of Cards. How many different compression options are there along that spectrum?
It really depends on who you're streaming it from, basically, because a site that doesn't have a lot of experience in video, they might decide to just do a single encode, for example, and say, okay, everyone's going to get sort of this middle tier quality bit rate, so people on very high connections will be able to watch the video with no rebuffering, but the quality might not be there. But they don't want to make it too high because then people on lower connections, like on their phones or something like that, might experience too much rebuffering, right? And so, but then someone maybe, let's say like Netflix or someone with a lot more video engineering resources, they might decide to do a much larger ladder in which they generate essentially different versions of the video file for low connections to high connections. So someone on that T1 connection, there's a pretty close to lossless version, I would say like a 20 megabit version of the video file in which it's pristine quality and you will have no problem streaming it on your connection versus someone on that device. Let's say there's at the low end of the bitrate ladder, provided they have a 250 kilobit version that actually looks pretty decent because of the compression algorithm that they're using, and the quality might not be quite as good, but you'll be able to sort of stream it without any rebuffering as well. And so it's really sort of just maximizing the experience as far as things like startup time, rebuffering, quality, depending on like the situation that your audience is in.
You've mentioned this term bitrate encoding ladder a few times, and I think this means that for any given video title, you want a set of encodings for that video that can be delivered to target users given a user's constraints. So a ladder is an exploration of the trade-offs between bit rate and quality, I guess, because if you have a higher bit rate, that means it's going to be a bigger file, but it's also going to be higher quality. And if you have a lower bit rate, it's going to be lower quality, but it's not necessarily a linear trade-off scheme. Can you define the term bitrate encoding ladder a little bit more?
Yeah, sure. So basically, your description of it is pretty spot on. It's basically, there's these files called renditions, essentially, in which we're taking the original source file and creating another additional versions of them. And from pretty close to lossless down to lossy compression versions, in which the quality goes down. That's why you see things like JPEG artifacts, right, in sort of low quality video, because it has to do with not having enough bits for particular scenes, and basically you can't allocate enough bits to accurately encode what's going on the screen. So that's when sort of quality really starts to go down, when you don't have enough bits to fill out the details. You can put in as many renditions really as you want in a bitrate ladder. And so the renditions are defined as like the bitrate that you choose. So typically on the high end of a bitrate ladder might be something like 10 megabits. The thing is, no one really knows what a bitrate ladder should ideally look like. And the reason for that is because it changes really depending on the content. And so, some people use, 10 different steps in the bitrate ladder. Some people use 3 or 5 or, whatever. And Apple has sort of their recommendations for what a bitrate ladder should look like. And so a lot of people just use that, but it's really more general purpose than optimized for anything. So the encoding ladder that you provide to the end user is basically, they don't necessarily just choose one, two. There's something called an ABR algorithm that's built in as part of the player. So as your internet connection fluctuates, let's say you start off, as a high connection, then it will look for sort of the appropriate rendition in that bitrate ladder to pull, and it'll pull from the higher end. And if your connection drops, then it'll say, okay, our internet connection can't handle this rendition anymore. Otherwise, we'll experience too much rebuffering. And so let's go ahead and pull from the low end. That's sort of a fairly simplified view of how it works, in the sense that we send a manifest with different renditions, and on the client side, there's an algorithm that chooses the best rendition given your internet connection speed.
When I was in school, I learned about how entropy affects file compression. So that is to say that if you have two files that are the same size and you want to run a compression algorithm on each of those files, you won't necessarily get the same size of the compressed end result if there are different entropy rates in the bits within those files, because compression algorithms work based off of the patterns in the bits within a file. And this is why you said that you don't necessarily have a straightforward trade-off between bit rate and file quality that's uniform, because it's going to actually depend, your bitrate encoding ladder, the ideal bitrate encoding ladder is actually going to depend on the title of the movie, because different movies have different rates of entropy in the file itself. So if you have a movie that is like just two people talking in chairs sitting across from each other, like if we did the movie version of this podcast, that's not a very high entropy title. And so you could probably compress a whole lot of that information into a smaller file that would still be relatively high bit rate. Whereas if we took an action movie with all these cutscenes that's the same length as a movie of you and I talking to each other, that might be much higher entropy. Therefore, it's going to be more bandwidth intensive to encode it even to the same bit rate as that movie of me and you talking to each other. Is that an accurate description of the whole bitrate encoding ladder versus entropy thing?
That's definitely accurate. So, when you're talking about, right, like us just sitting here, let's say, talking a video of that, the things like the background, for example, wouldn't change. Right? Like, and the background probably be very simple. It'd be white walls or something like that. And so the compression algorithm is able essentially to sort of look at that and say, like, all right, like these pixels, they're frame from frame, they're staying the same essentially, and we don't really need to allocate a lot of bits to figuring out, to like creating these frames. And so we can put more detail into the parts that do change, and sort of just the overall number of bits that are required to reconstruct the video file is fairly low, versus if there's a lot of motion, or if there's just a lot of changing detail, a lot of different scene cuts, then you can't really extrapolate a lot of information. You have to just use the raw bits to reconstruct those fine details. And so if you look at watch video that's streaming online, oftentimes it's a little hard to tell sometimes, but if you watch for it, you can really see the JPEG artifacts sort of pop out in sort of fast motion scenes that maybe is in an otherwise fairly high quality video, because during those fast motion scenes, essentially it cannot sort of cheat and extrapolate any information like it has been in sort of stiller motion scenes. And that's when you get sort of those like blocky frames. And a lot of people don't notice that if they're not looking for it, especially if it's just like a single maybe scene in a longer video. But it definitely becomes a lot more noticeable if you get more and more complex scenes or more and more motion scenes, especially in things like sports videos or, like you said, action movies.
Over the last 2 years, I spent much of my time building a video product. We had issues with latency, unreliable video playback, codecs. I was amazed that it was so difficult to work with videos. As it turns out, video is complex, and figuring out how to optimize the delivery of video is not easy, especially since there is both mobile and desktop, and mobile users might not have as much bandwidth as desktop users. If you're an engineer working on a product that involves video, you just don't want to think about any of this. I can tell you that from firsthand experience. And that's why Mux exists. Check out mux.com and find out how Mux makes it easy to upload and play back video. Mux makes video hosting and streaming simple. And today you can get $50 in free credit by mentioning SE Daily in the sign-up process. Even if you aren't working on video right now, if you think you might work with video in the future, Mux is a really useful tool to be aware of. Check out mux.com, and if you're an engineer who's looking for work, you can also apply for a job at mux.com. On Software Engineering Daily, we've done 2 shows with Mux, and I know that Mux is solving some big difficult problems involving lots of data and large video files. To find out more, you can go to mux.com. You can get $50 in free credit by mentioning SE Daily, and you can apply for a job if you're interested in working on some of these large challenges. Thanks to Mux for being a sponsor of Software Engineering Daily. This gets us to this method called per-title encoding. Netflix developed this method for encoding, for compressing their bitrate ladders, for defining their bitrate encoding ladders. Netflix developed this method called per-title encoding. Explain what per-title encoding is.
Yeah, so per-title encoding is basically, people do per-title encoding in different ways. So let me define sort of the way that Netflix does it, because they were really the first ones to do it and to sort of announce it to the world. And so the way that they did it was, first they defined their own type of quality metric for video. So there's a bunch of different quality metrics for video in order to judge what's the amount of loss that occurs from the source video. And that alone is sort of a whole area of research that's fairly complex. The sort of golden standard of figuring out what quality video is basically just, asking someone, right? As having a human eye judge the quality of video, because it's a fairly subjective thing. You can't just judge based off of sort of the amount of blur or the amount of artifacts or things like that, because, for example, with things like blur, sometimes the blur is supposed to be there, or sometimes with like film grain, there's sort of this noise that's actually part of the movie, and you can't necessarily judge that as lower quality. And so we only really know that because, as human beings, we can discern that difference, but it's very hard for us to put that as far as in a quality metric. So Netflix created their own quality metric called VMath, and they basically used machine learning algorithm to sort of approximate VMath fairly closely to what's called a mean opinion score, which is the golden standard of just having lots of human beings look at video and sort of rate it, essentially. And VMath is considered now probably the best or one of the best quality metrics when judging video. And then they took VMAP and they said, okay, we're going to take all these different types of video and we're going to do thousands of different encodes on it based off of the resolution and what the bitrate is. And so that's sort of the axes of a bitrate ladder, is deciding, one, what bit rates you want to put into the rendition, but also what resolution you want to encode at that particular bit rate. And so you can imagine if you're stepping up from 250 kilobits up to 10 plus megabits or 20 megabits if you're encoding at Ultra HD video, and you're testing 5 to 10 different resolutions, right, for each one of those, you start doing thousands of encodes for every single video, which Netflix is able to do because they have the resource to do that, but that's very, very expensive, right? And so for each of those encode, then they run VMAF on it, which then says, okay, at this particular bit rate, this particular resolution is the highest quality. And so that's the bitrate resolution pair that we're going to choose for this bitrate. And then they move on and do that for every single bitrate. And after they've done that, they know, okay, at each particular bitrates, these are the resolutions that we want. So that's the encoding ladder we're going to do for this video, which means at any particular bitrate, they know with confidence that they're giving the highest quality possible to the end user, subject to how accurate VMAP is. Because sometimes people view VMAP as sort of, because it's very, very good, as sort of like the end all be all quality metric, it's still an approximation of quality. So it's very, very likely that they're giving the highest quality resolution or bitrate to the end user, which means that they can do a lot of really interesting things. Either they can give you better quality than sort of anyone else is providing for a video, or they can say, okay, our quality is already pretty good. Our quality really doesn't change much, but now we can also optimize bit rates. So let's say, you get diminishing returns on the bitrate ladder as far as quality goes at a certain point. So instead of encoding things at particularly high up along the bitrate ladder, we can get away with 99% of the quality with half of the bits, which means you need half the internet speed connection to watch Jessica Jones in HD, essentially. So it leads to a lot of really interesting possibilities like that.
Does per title encoding ultimately boil down to how complex and how entropic the video file is, or are there different types of complexity that can exist in a video file?
Yeah, for sure. So they started off with per title encoding. They've actually moved on to something else called per shot encoding recently. But essentially, they look at how the complexity within a single video, right? So it's just on average in a way, and say, okay, how do we make sure that the resolution for this bitrate is optimized on average across the entire video, which means that if you have a video that switches pretty drastically between, let's say, high entropy versus low entropy scenes, it might not work as well, because then you're not optimizing for the individual scenes. But in order to optimize for individual scenes, you imagine for a single video, they were doing thousands of encodes. If you have a couple hundred scenes in a movie, right? It gets to an order of magnitude that even Netflix can't really scale that affordably. So they have to do some other things to make that work. Okay,
so in order to get to the machine learning part of this conversation, I think we need to explore why Mux's product is different than Netflix. Why there's a different use case, and the per title encoding, the slow per title encoding, which Netflix's per title encoding is slow in order to run it for all their movies. It's just a different use case than Mux. So can you kind of explain why is it okay for Netflix's per title encoding to be slow to run, and how does that differ from the context that Mux is doing encoding in?
Yeah, so doing that many encodes is very expensive to do, and because Netflix has a fairly relatively small video library there and 5,000 EC2 instances that they can spin up for this, they're able to do that in a scalable way. For Mux, we expect to, because our video product, we hope one day will scale to billions of videos. We can't do thousands of encodes for every single video that's uploaded. So in order to do that, we have to approximate per title encoding through machine learning. That's the only way that can really scale. Another issue is that we do what's called just-in-time encoding, in which the encoding for a single video happens much, much faster than real time, because we sort of cut up the video and do a parallelized encode across the video. So when you upload a 2-hour movie, let's say, to Mux, it doesn't take a few seconds, maybe a minute to encode the entire movie. And so we don't want to add on unnecessarily long processing times to do per title encoding, because as part of per title encoding is essentially 2 steps. First you do the encode, and then you run VMath on it. If we were to do that, let's say for a 2-hour movie, it would take probably about 24 plus hours to do, and even in a parallelized environment. So it takes a really, really long time to do per title encoding, the way that Netflix is doing it. Instead, we decided to say, okay, what if we created a type of video classification algorithm instead, to approximate the complexity of what's happening in a video, right? Because in a lot of ways, if I was to tell you, okay, well, like we were doing before, this video is an action movie, with sort of these type of scenes, you don't really, versus like this movie is like a rom-com or something like that. You don't really need to know, even really see the scenes to know that, okay, the action movie is going to have higher complexity, right? And so in order to then say, okay, we know that this is an action movie, we know that these are sort of the type of scenes that are in it, can we then approximate a bitrate ladder from that instead, which is a lot faster and more efficient to do for a video than to analyze the frames sort of individually bit by bit, which is what we would have to do, if we were to sort of take the more brute force method of per title encoding that Netflix started.
So outline the plan to increase the speed of the encoding in a little bit more detail, and explain why deep learning was a potential solution to this speed up.
Yeah, so essentially the steps that we take for this is, first we take a video and we do look at the individual frames for it, but we do sort of a sample of the frames, and we use what's called transfer learning, in which we're taking embeddings, feature embeddings from the frames to get an approximation of what is the content of the video. Essentially what our model does is it's a content classifier that then embeds the content into a very large feature space that we then map to optimal bitrate encoding ladders. Okay, so our bitrate encoding ladder is around 50. There's 50 rungs in the ladder, let's say. So going from 250 kilobits up to 10 megabits, right? And you can sort of think of the end output of that to be at each rung of the ladder what the optimal resolution is, right? And so that's what the model wants to predict at the end of the day. It's trying to predict essentially a sequence of resolutions in 50 steps. And that is a much faster process to take, let's say, frames of an image and move it through first a sort of image classification model, and then into a video classification model, and then into sort of a predicted 50-step sequence output, because training that we do for this model is done on actual per title encodes. So we've created this database of videos in which we have done these manual encodes in the same way that Netflix does, right? So let's say like for the action, we've done lots of different action movies, and we've done the sort of Netflix style per title encoding to say like, okay, these are the 50-step sequences that these different types of action movies look like. And so if we've done the optimal encoding for Terminator 1, right? And then someone uploads Terminator 2, right? The encoding ladder is probably going to look pretty similar to it. And so we don't necessarily need to do per title encoding again for Terminator 2. We can approximate that as saying, using this video classification system, and which works in seconds rather than in hundreds of hours.
Part of this process is being able to have a classifier that can classify the videos as effectively being highly complex or low complexity. Is that right? Is that what the classifier is doing?
Yes, it's not a direct measure of complexity. It's more of a measure of what type of video this is. And that is often a proxy for complexity.
Yeah.
Especially since the way that when you do the per title encoding and it becomes grouped in different types of encoding ladders, and that is the state in which you're trying to predict, then the feature space in which we've embedded the videos, then they become grouped around sort of tiers of complexity, which is what we end up seeing. But it's not what we are directly trying to classify the videos into.
What are the features that you're developing measurements for each video? What are some of these features? Can you put them into words, or are they inarticulable?
It is a black box model in which we're not predefining the features, but rather we create a model architecture and choose a layer within the architecture in which we think it makes sense to pull out that feature. And so some of the considerations that go into that is you don't necessarily want too big of a feature space, for example. If you have too high of a dimension for your feature space, then nothing can sort of coalesce around each other. You can't really get any sensible clusterings, or you need just an enormous amount of data in order to cluster around, a feature space of very, very high dimensions. And at the same time, if you want a feature space that's too small, or you get a feature space that's too small, then you might have too much overlap between sort of different types of complexity between videos.
There is a YouTube data set that you used called YouTube 8M. Describe why this data set was useful and what it does and what you used it for.
The YouTube 8 million data set was really important for us to pre-train our model on. Basically, the YouTube had already done a lot of video classification and open sourced it through this data set in which different YouTube videos had been, in some supervised way, have been labeled into different categories. I think it was about 4,700 categories that the data set that was released last year had. And so not all the labels were perfect because they weren't hand labeled, but they were essentially graded against a hand labeled data set to sort of boost the accuracy. And they allowed us to basically have a model that was pre-trained on different types of video classifications that you see on YouTube, which then, taking that pre-trained model, we're able to much faster train that in a way that instead of classifying just on sort of the content, classified on the bitrate encoding ladder. So we use transfer learning essentially multiple times during the creation of our per title encoding model, and that was one of the sort of critical steps was for us to, instead of training our own video classification model from scratch, which would require thousands of hours of machine time, we were able to get a really nice data set from YouTube that allowed us a really good starting point to then train on our own data set of encoding ladders. Explain what transfer learning is. Yeah, so basically, when you have a machine learning model, a lot of the things that one machine learning model, particularly deep learning, is where transfer learning is used. When you have sort of trained a very, very deep model, let's say, the last few layers of that model are often relevant to let's say, other models that might not have the same end goal, but might require the same type of high-level classification. So, for example, it's used a lot in image classification, right? Let's say that a very popular image classification model is called Inception. And so Inception, the way that a deep learning model works is it takes low-level features and then creates high-level features as it moves up in the layers until finally it gets to the classification layers in which it puts labels on things. So, for example, when you give a image to Inception, first thing it does, it might say like, all right, let's find where like all the lines are, right? And all the edges are. And okay, here are the edges. And from that, let's figure out like where the shapes are, right? So here's a circle, here's a square, here's a couple cylinders, whatever. And then on the next layer up from that, it might say, okay, let's combine these shapes. And so like this circle and these cylinders, they kind of go together. at the very, very last layer, it says like, okay, when circle and cylinder goes together like this, that's a table, right? And so maybe we want, instead of something that labels like tables, we want it to label faces instead, right? Well, training inception is a very costly and time-intensive task. And so in order to detect faces, we have to detect things like edges and shapes. And so we don't necessarily need to retrain all of inception, because it essentially is able to have that sort of edge and shape detection already built in. So we just sort of cut off the end of inception where it says, okay, let's label this circle and cylinder as a table. And instead we say like, okay, let's add a few more layers and instead show a bunch of like faces instead, and it can combine these shapes and edges into a face detection model, and you can do that much, much faster. So that's essentially what we do with image classification using the YouTube model, the YouTube 8 million data set, is say, okay, instead of labeling YouTube videos, right, you've seen tons of videos and have been able to like process all the low features of the video. Now we just want to direct that into classifying bitrate encoding ladders rather than high-level YouTube classification.
In today's fast-paced world, you have to be able to build the skills that you need when you need them. With Pluralsight's learning platform, you can level up your skills in cutting-edge technology, like machine learning, cloud infrastructure, mobile development, DevOps, and blockchain. Find out where your skills stand with Pluralsight IQ, and then jump into expert-led courses organized into curated learning paths. Pluralsight is a personalized learning experience that helps you keep pace. So get ahead by visiting pluralsight.com/sedaily for a free 10-day trial. And if you're leading a team, discover how your organization can move faster with plans for enterprises. Pluralsight has helped thousands of organizations innovate, including Adobe, AT&T, VMware, and Tableau. Go to pluralsight.com/sedaily to get a free 10-day trial and dive into the platform. When you sign up, you also get 50% off of your first month. And if you want to commit, you can get $50 off an annual subscription. Get access to all three: the 10-day free trial, 50% off your first month, and $50 off a yearly subscription at pluralsight.com/sedaily. Thank you to Pluralsight for being a new sponsor of Software Engineering Daily. And to check it out while supporting Software Engineering Daily, go to pluralsight.com/sedaily. Okay, let me see if I understand this right. You've got this YouTube data set of 8 million videos, and those videos are labeled with certain entities that are in the video, like cats and baseball bats and sunrise and cup of coffee, all these different things. And you can take those embeddings, the labeled entities that are in videos, and you can correlate them with ideal compression ladders or bitrate encoding ladders for a given video. So if a video has a cup of coffee and a cat and a baseball bat in it or something like that, maybe you can correlate a certain type of bitrate encoding ladder with that. Am I understanding it right? Like, is that kind of what you're doing?
Yeah, absolutely. So it's not really measuring the complexity of the video directly. It's more saying, this is the type of content that the video has. And often that's highly correlated with the complexity. Knowing that it's a video of two news anchors talking, right, is sort of another way of judging complexity in the video without actually directly measuring the bits, which is much more time intensive and difficult.
Two news anchors talking to each other, low complexity, the background is never changing. On the other hand, explosions and cars driving fast, that is going to be a high complexity scene, and you're going to need a different bitrate ladder for the low complexity scene versus the high complexity scene. Right,
exactly. I mean, imagine, if I give you a bunch of videos to label complexity on, essentially what you would be doing, you wouldn't, be measuring changes, like how many bits are in the frame and how do they change and everything like that. You'd be saying things like, okay, here's the number of scene changes, and there's explosions happening, and there's this person running, right? You'd be sort of labeling the video in these high dimensional features of the video, and so that's the direction that we wanted to do with our deep learning approach, rather than sort of directly measuring using VMath and encodes.
So if we have our video of you and I talking to each other in chairs, just in a room, and that should probably be measured to have complexity that's similar to the two news anchors talking to one another, if the two news anchors was in the training data set for the model. So what would happen with our brand new video? How would that get ascribed with the correct complexity level and the correct bitrate encoding ladder?
Right. So you imagine, essentially, let's say it's seeing a video of two news anchors, and then what sees the video of us talking, right? The visual features of that are fairly close. It's fairly related. It's a lot of those features then would be next to each other within the feature embedding space, and because of that, it would output a similar encoding ladder to the news anchor. And this sort of has a trade-off in that maybe it's an approximation, right? So that maybe it might be a bit off. It might be slightly not optimized in certain points of the bitrate ladder, but it should still be fairly close. But sometimes that approximation is really good when we see a type of video that we've never seen before, or something that we've sort of seen similarities of between two different types of video. So for example, let's say we have in our data set, where we've done the actual encodes, we have a football game, right, an NFL game, and we also have video games as a category. And then someone uploads like a Madden game, right, in which it has sort of video game features as well as actual football game features as part of that. Well, the machine learning model should be able to say like, all right, there's features that are sort of related to this cluster and related to this cluster, so let's approximate and let's put it in the middle, right? And so it should output an encoding ladder that is sort of a blend of both those categories, which hopefully would be then pretty accurate in terms of being the optimal encoding ladder for a new category.
How did you measure the effectiveness of this deep learning solution, of this machine learning training process for doing per title encoding?
We had to do a lot of actual brute force per title encodes, in which we knew what the optimal encoding ladder was, and therefore we could measure it and say at these particular bit rates, these are the right resolutions. And so we do a fairly standard training test split in our data set, in which we evaluate our deep learning approach on the types of encoding ladders as output, and we measure against what the actual level is. And so for our evaluation, we saw that along all 50 rungs in the ladder, it was getting between 70 to 80% of the rungs correctly. But that's actually because we don't choose all 50 rungs. Sometimes that doesn't necessarily mean 70 to 80% as good. It really depends on how you choose the renditions from the bitrate ladder, as well as where it's off by. Because if it's off by a few bit rates at sort of high end, but we don't even look at the high end, let's say for a particular video, it might be 100% accurate, or it might be 50% accurate if it's off in sort of a bad spot along the ladder. So that's sort of another issue that we have to optimize for, and have to use additional machine learning techniques in order to figure out what the best rate to choose that rendition is. Is
this running live today for you?
Yeah, it's in production for us. So if you go to mux.com and within our API, you set per title encoding equals or to true in your API post, then it will run our per title encoding on your video, and you can see sort of the optimized encoding ladder as well that it uses versus sort of the standard set, which is we use sort of Apple's recommended, pretty close to Apple's recommended ladder for sort of the standard encode.
So what was the length of time from ideation to deployment for the full soup to nuts, I guess, architecture, whiteboarding scenario to actually deploying this per title encoding algorithm?
It probably took about, from ideation, I would say about 6 months before we got the first version out into production. It's definitely, the work on it definitely hasn't finished, because as we're still expanding the data set, sort of expanding edge cases for the video. So there's still a lot of work that we want to do on it, but we're pretty happy in the state as currently in this initial version that we launched.
Mux is a fairly young company, and a 6-month project for improving the compression ratio for videos, or improving the compression ladder algorithm, I guess you would say. It's a large investment. Why was this project so worth working on? Why is it so important or so core to Mux that it was worth putting 6 months into devising this deep learning algorithm and doing all this engineering around just making a better encoding solution?
Well, we really view it as the first step for a lot of future features that we want to include to Mux. It's definitely not sort of a siloed project in which like we implement per title encoding and that's it. It really leads to a lot of future projects, and a big focus of where we want Mux Video to be in the future is sort of dead simple API for engineers to use that doesn't just give you sort of standard video, versus if you were to implement it yourself, and put all the plumbing together for your video project, but really just a product in which you get video that would normally require, a whole team of engineers from Netflix to implement. And instead, it takes you a few minutes to set up, and you get sort of the highest quality video possible, right? And you get all these machine learning features that are built into it so that that the quality is optimized. You have different features that allow you to, save space, the amount of storage, have optimized delivery of your video. And so there's a lot of sort of future projects that we want to build on top of per title encoding. So for example, per shot encoding is something that I mentioned earlier, in which not only is you essentially take this model and you, instead of looking at the video, from end to end, you run the optimization for every single scene. And so that really makes a huge difference, because that every single scene that you look at within a video is sort of the highest quality possible for what your user's internet connection will be. And so it's definitely not just a 6-month project for us. It's sort of just it's an ongoing project in which we want to make Mux Video sort of the best quality, the best video product available to engineers out there.
What I liked about studying this project was that it exemplifies a lot about where we are in software engineering today. So first of all, you've got great machine learning frameworks that you can do all this in quite productively. I mean, 6 months is it's a long time, but it's still much more rapid than you would have without a deep learning framework to be using. Not only that, you're leveraging Netflix's research in the per title encoding concept and their willingness to talk about that. And they have a blog post from 2015 or 2013 or something. You also leveraged the YouTube data set, the YouTube 8 million labeled data set that YouTube was kind enough to put out there. You used transfer learning on top of that. And I like that it's just, this project is this example in time of all these different trends and these different companies sort of being willing to put stuff out there that other people can leverage. It's kind of positive sum ecosystem from a lot of different angles on this one. I know we're near the end of our time, but did you have any broader insights about the state of software engineering, the state of machine learning when you were working on this project for the last 6 months?
Yeah, I mean, definitely implementing this project certainly felt like, standing on the shoulders of giants as far as how much we leverage from open source projects. We've talked to Netflix, some of their engineers, about how they use VMath and how they do per title encoding to try to get more insight into our system. And everyone, the whole machine learning environment, I think it's great how much of a focus there's around open source projects. I know that for me personally, there was a lot of different options I felt when we were evaluating how to do this, and the amount of data sets out there, the amount of sort of willingness between different companies to sort of share the insights they've gotten around video classification is just tremendously helpful. In fact, there's a new Kaggle competition that just opened on a few weeks ago, in which YouTube had published an update to their data set. So their data set now has better labels, it's a bit more accurate. And on Kaggle itself, which is owned by Google, a lot of people share sort of the different types of models that they're working on. So it's great to sort of be able to go talk to the community about what's happening in video classification, and to see companies like Google publishing these data sets for free that would, if we were to do it ourselves, it would just be incredibly expensive. And I don't think it would really be possible in this state. One thing that I did feel, though, in terms of looking at the sort of recent advancement of different video classification and computer vision projects, is that there definitely seems to be sort of more of a plateau as far as the actual deep learning techniques happening. If you look sort of a few years ago, based off of different computer vision deep learning techniques, that as far as model architectures go, there was sort of a lot of different shifts, a lot of new papers being published as far as what people were using and implementing. I feel like that definitely sort of has coalesced a bit around certain machine learning techniques as being sort of the main ones that people go to, and really just smaller iterations, improvements on those techniques now, rather than sort of big leaps forward like we were seeing 2-3 years ago. That's sort of been an interesting development, I think, to see over the past year.
Ben Dodson, thank you for coming on Software Engineering Daily. It's been great talking to you.
Thank you. Thank you for having me. It's been fun.
GoCD is a continuous delivery tool created by ThoughtWorks. It's open source and free to use, and GoCD has all the features you need for continuous delivery. Model your deployment pipelines without installing any plugins. Use the value stream map to visualize your end-to-end workflow. And if you use Kubernetes, GoCD is a natural fit to add continuous delivery to your project. With GoCD running on Kubernetes, you define your build workflow and let GoCD provision and scale your infrastructure on the fly. GoCD agents use Kubernetes to scale as needed. Check out gocd.org/sedaily and learn about how you can get started. GoCD was built with the learnings of the ThoughtWorks engineering team, who have talked about building the product in previous episodes of Software Engineering Daily, and it's great to see the continued progress on GoCD with the new Kubernetes integrations. You can check it out for yourself at gocd.org/sedaily, and thank you so much to ThoughtWorks for being a longtime sponsor of Software Engineering Daily. We're proud to have ThoughtWorks and GoCD as sponsors of the show.
Wow!